All right, let's dive into some seriously cool quantum physics. If you've been following along with us, you know we've been exploring quantum materials.
Right.
And today we're going to tackle something called quantum spin liquids.
Yeah, these things, they really kind of break all the rules.
They do.
You don't see magnets here, even at like super low temperatures.
So we're talking about materials that stay magnetically disordered, even in conditions where, like, everything else wants to line up neatly.
Exactly.
One of the materials scientists are looking at is built on a structure called a Kagome lattice.
Uh-huh.
K3, HOTP2 to be exact.
Yeah.
I know it's a mouthful.
It is a mouthful,
Yeah.
but it's a fascinating structure, though. Think of a repeating pattern of triangles connected at their corners.
Hmm.
And it's on this lattice that the spins in that material, K3, HOTP2, perform their strange, disordered dance.
So to try and understand this dance, scientists have pulled out some pretty high-tech tools. We're talking magnetic susceptibility measurements,
Right.
muon spin relaxation,
Yeah.
and neutron scattering, like a whole forensics team for quantum material.
Exactly. Each technique provides a different clue.
Mm.
So magnetic susceptibility measurements showed no magnetic transitions even at extremely low temperatures, which already hints that something unusual is going on.
Okay.
Then muon spin relaxation revealed that there are fluctuating magnetic fields within the material,
Mm.
suggesting a very dynamic spin environment.
So we're seeing evidence of spins that just can't seem to make up their minds.
Yeah, pretty much.
They're constantly fluctuating, not settling into any kind of ordered pattern.
Yeah.
Okay, so what about neutron scattering? What did that reveal?
So neutron scattering, that gives us really a crucial piece of the puzzle. What it showed was a diffuse scattering pattern. Now, in a normal magnet, you'd expect to see sharp, defined peaks because those spins are arranged in a precise order.
Right.
But with this material, Q3HOTP2, the scattering was all over the place. It's like trying to take a picture of a crowd that's constantly moving, everything's blurred.
Okay, so if diffuse scattering is like a blurry picture of a restless crowd, is that like the defining characteristic of a quantum spin liquid?
Yeah, you could say that.
Is that how scientists know they found one?
It's definitely a strong indicator, yeah. It tells us that even though the spins are correlated, they lack that long-range order that you would find in a typical magnet.
Mm.
They're linked in a way, but not in like a neatly aligned fashion.
So we've got this strange material, Q3HOTP2, acting in ways we wouldn't expect. We've seen the evidence.
Right.
But how do we make sense of it all? What's the theoretical explanation for why these spins just refuse to chill out?
Well, that's where things get even more interesting. There are a couple of prominent theories trying to explain this unusual behavior.
Okay.
One of them is the resonating valence bond theory, RVB theory for short.
Okay, let's unpack this RVB theory. What's the key idea here?
So imagine the spins in the material forming pairs,
Oh.
but instead of staying with the same partner, they're constantly swapping. It's like a never-ending square dance where everyone is switching partners all the time. And it's this constant partner swapping that prevents the spins from settling down into a stable magnetic order.
So it's like the spins are in this wild, entangled dance, never able to form a static pattern.
Yeah, exactly.
That's a pretty cool way to visualize what's happening. But isn't there another theory out there?
Yeah.
Something about Dirac fermions.
Yes, that's the Dirac spin liquid model. It's a bit more abstract, but equally fascinating.
Okay.
So think of the spins as behaving like tiny massless particles called Dirac fermions whizzing around on this Kagome lattice playground.
Hold on. Massless and whizzing around.
Yeah,
We're talking about spins, right?
right.
How can they act like particles?
Well, that's the beauty of quantum mechanics. Things get a bit fuzzy at that level.
Hmm.
In this model, the Kagome lattice structure allows these Dirac fermions to move freely, preventing the spins from settling into a static arrangement.
Hmm.
It's like the lattice itself is designed to keep things in constant motion.
Okay, so we've got these two competing theories, both trying to explain why these spins just can't seem to sit still. But how do scientists know which theory is correct?
Right.
Are there experiments that can, like, differentiate between the two?
Yeah, that's a great question, and it's something that researchers are actively investigating. It might be that both theories capture certain aspects of what's happening,
Okay.
or perhaps there's an even more complete theory waiting to be discovered. It's a bit like having two different sets of blueprints for the same building.
Okay.
They both describe the structure, but highlight different features and construction methods.
Mm-hmm.
Scientists are still trying to figure out which blueprint, or maybe some combination of the two, thus reflects the reality of these quantum spin liquids.
So it's a scientific mystery.
Yeah.
But that also means there's a lot of exciting research going on. What are some of the biggest challenges researchers face when studying these materials?
Well, one of the main challenges is actually creating these quantum spin liquids in the lab. They often involve complex synthesis techniques that require a high degree of precision and control. It's a bit like trying to assemble a microscopic jigsaw puzzle with pieces that are constantly vibrating.
I can imagine. And then once you've actually managed to synthesize the material, you still have to figure out how to study it. We talked about some of the techniques,
Right.
like neutron scattering and muon spin relaxation, but I imagine those aren't exactly plug and play.
Yeah, you're right. These techniques require specialized equipment and expertise.
Right.
And even then, interpreting the data can be quite challenging.
Mm.
You're essentially trying to infer the behavior of these tiny spins indirectly based on how they interact with other particles or fields.
Mm.
It's a bit like trying to understand a complex dance routine by only looking at the shadows it casts on the wall.
It's a great analogy. It sounds like studying quantum spin liquids requires a unique combination of experimental skill and theoretical insight. But all this effort must be driven by some pretty compelling potential applications, right?
Yeah, absolutely.
We've hinted at quantum computing, but what else is on the horizon?
Well, quantum computing is definitely one of the most exciting prospects. Imagine harnessing the power of these entangled spins to create incredibly powerful quantum computers that can tackle problems that are impossible for even our most advanced supercomputers today.
That sounds revolutionary. But how would quantum spin liquids actually be used in quantum computing? What makes them better than the qubits we're using now?
One of the key advantages is their stability. Remember, these spins are inherently entangled and resistant to disruptions.
Right.
Traditional qubits, on the other hand, are extremely fragile and susceptible to errors.
Okay.
Quantum spin liquids could offer a more robust platform for quantum computing, paving the way for faster, more reliable quantum devices.
That's incredible. It sounds like we're talking about a whole new level of computational power.
Yeah.
But what about other applications? We hear a lot about superconductivity these days. Any connection there?
That's another area where quantum spin liquids could play a significant role.
Hmm.
Some researchers believe that understanding the mechanisms behind these exotic materials could provide insights into achieving high-temperature superconductivity.
Okay. For those of us who haven't been brushing up on our condensed matter physics, remind us what superconductivity is and why we should be excited about it.
Sure. So superconductivity is a phenomenon where certain materials at extremely low temperatures can conduct electricity with absolutely no resistance.
Okay.
Imagine a world where energy flows freely through power grids without any loss, powering our cities and industries with unprecedented efficiency. Or imagine super fast, ultra efficient electronics that don't generate any heat.
Now that's a future I can get behind. Lossless energy transmission, super efficient electronics. It sounds almost too good to be true. But if quantum spin liquids can help us achieve that, then all this research would be more than worth it.
Exactly. It's not just about satisfying our scientific curiosity. It's about potentially revolutionizing technology as we know it. And the possibilities don't end there. There's one more potential application that's particularly intriguing, though it's still very much in the realm of speculation.
Okay, you've got my attention. What is this mysterious application? Don't hold out on me.
Well, some physicists believe that quantum spin liquids could provide insights into the nature of dark matter, the elusive substance that makes up the vast majority of the matter in the universe.
Wait, dark matter? The stuff we can't even see or interact with directly. How could these quantum materials possibly be connected to something so vast and cosmic?
It's a fascinating idea, isn't it? Remember those spin excitations in quantum spin liquids, the ones that behave like Dirac fermions?
Yeah, those massless particles zipping around on the Kagome lattice. I thought those were just a theoretical construct to explain the spin behavior.
Well, some physicists have proposed that dark matter itself might be made up of particles that interact very weakly with ordinary matter, much like those spin excitations in quantum spin liquids.
So you're saying there could be a parallel between the way these spins behave in these exotic materials and the way dark matter particles interact with the rest of the universe.
Exactly. It's a bold idea, and it's still very early days in terms of research, but it's an intriguing possibility that could potentially link the study of these tiny quantum systems to the largest scales of the cosmos.
That's mind-blowing. So we've gone from these strange, magnetically disordered materials to potentially revolutionizing computing unlocking new forms of energy transmission and maybe even helping us solve the mystery of dark matter. It sounds like quantum spin liquids could be one of the most important areas of research in the 21st century.
I think you're right. We're just beginning to scratch the surface of what these materials can teach us about the nature of quantum matter and its potential to transform our world.
Yeah, it's incredible to think that something so seemingly esoteric as quantum spin liquids could have such profound implications for our understanding of the universe and the technologies we might one day create.
Yeah, definitely.
It really highlights the interconnectedness of science, how discoveries in one area can ripple out and impact fields we might never have imagined.
Absolutely. And it's a reminder that we're still just beginning to unravel the mysteries of the quantum world. Who knows what other surprises and breakthroughs await us as we continue to explore these uncharted territories.
Yeah, it's almost like we've stumbled upon a whole new set of rules, like
Yeah.
a new language for describing the universe at its most fundamental level.
Yeah,
But I have to admit, sometimes I feel a little lost in translation. All this talk of spin excitations and direct fermions can make my head spin, no pun intended.
I understand.
Yeah.
It's easy to get caught up in the technical jargon and abstract concepts, but at its core, the beauty of these quantum systems is their sheer weirdness, their
Yeah.
ability to defy our classical intuitions about how the world should work.
And it's that weirdness that makes it so captivating. It's like we're peeking behind the curtain of reality and seeing the universe in a whole new light.
Exactly. And it's that sense of wonder and exploration that drives scientific discovery.
So, for those of us who are not quantum physicists, what's the key takeaway from all of this? Why should we care about these strange, magnetically disordered materials?
I think the main takeaway is the sheer potential of these materials to transform our world. We've talked about quantum computing, superconductivity, and even dark matter research. But those are just a few examples. As we delve deeper into the realm of quantum spin liquids, who knows what other applications we might uncover?
It's almost like we've been given a glimpse into a future where the boundaries between science fiction and reality begin to blur. We might have quantum computers that can solve problems previously thought to be intractable. We might have energy grids that operate with near perfect efficiency, revolutionizing our energy infrastructure. And we might even gain a deeper understanding of the very fabric of the universe thanks to the insights gleaned from these unusual materials.
And all of this stems from the study of these tiny interacting spins that refuse to behave like anything we've ever encountered before. It's a testament to the power of scientific curiosity, the drive to understand the world around us, even when it leads us down seemingly strange and unfamiliar paths.
Well, I think it's safe to say that our deep dive into the world of quantum spin liquids has left us with more questions than answers. But it has also ignited a sense of wonder and a thirst for further exploration. I, for one, am eager to see what new discoveries emerge from this fascinating field in the years to come.
Me too. And for anyone listening who shares that same curiosity, I encourage you to dive deeper into the world of quantum spin liquids. There are countless resources available online and in libraries. Read articles, watch videos, and don't be afraid to ask questions. Who knows, maybe you'll be the one to make the next groundbreaking discovery.
That's a great point. This deep dive has been an incredible journey, but it's just the beginning. The world of quantum materials is vast and full of mysteries waiting to be unraveled. So keep exploring, keep questioning, and keep that curiosity alive. And until next time, keep on learning, friends.